I welcome everyone for the present session. Today I will be discussing about the introduction to the quantum computation. So moving on, what is exactly this quantum computation, quantum computing, and how is this quantum computing different from the existing binary or the digital computing world? So first of all, basically what is exactly a quantum? The quantum is the minimum amount of physical entity that is involved in an interaction, maybe in terms of communication, maybe in terms of the movement of data or the signals. And in plural, the quantum is called as a quanta. And this is a new model of computing and which is actually based on the quantum mechanics and which involves the quantum circuits, quantum Turing machines, etc. And it is more powerful than the conventional models which we are using in the current day. So the basic difference between the quantum computer and the classical, the binary computer which we are using in our day-to-day life. So this quantum computer uses the quantum mechanical phenomena to perform operations on data through devices such as superpositions and entanglement. So we know when we speak about a binary computer, we have two states, 0 and 1. So here also in quantum computer, we have the two states, but those two states will use superposition and entanglement. That is nothing but, we can call it as spin up and spin down, where we are going to get multiple states with those two bits. Whereas coming to the classical binary computers, we all know that these computers uses voltages flowing through circuits and gates, which can be calculated entirely by the classical mechanics. So then what is the need of going for this quantum computing where the digital computers or the binary computers are used everywhere in every applications and every industrial sector or every sector wherever we need computing. So in simple to answer, it is the need for the speed. So the classical digital computers, they are suffering with a bottleneck problem with the underlying electronics that which we use. So the digital computers are actually experiencing the bottleneck with respect to the Moore's law, which says that the number of transistors on a chip doubles every 18 months. And the microprocessor circuits that which we use actually will measure an atomic scale by 2020 to 2030. And the downscaling of this particular circuit board's layout or the components is leading to discrepancies, which generates huge heat and which makes shut out of those circuits. The copper traces are actually crystallizing and actually going for the shorting out. The emergence of quantum phenomena such as electronics tunneling through the barriers between the wires that which we are using nowadays. And the basic shortcoming with the digital computer is the serial processing. That is, it can process only one operation at a time. And for an example, a 64-bit classical computer operates speed measured in gigaflops, that is a billions of floating point operations per second. So this is what exactly the limitation, but the complex programming or the complex applications require more power, more processing power than this. So when we look at the quantum computer, it harnesses the power of atoms and molecules and to perform the memory and the processing tasks. Majorly it supports the parallel processing where millions of operations can be done at a time, which is actually not possible with the existing classical digital computer. So for an example, a 30 qubit quantum computers are equal to the processing power of conventional computer that is running at 10 teraflops, that is a trillions of floating point operations per second. So here we call the quantum bit as qubit over here. So we can harness the hundreds of times of speed by using a normal quantum computer, which is actually not possible with our existing personal digital computer. So moving on, how basically the classical binary bits are different from the quantum bits. As we already know that a classical binary computer uses two basic states, that is off and on, or 0 and 1, and they're actually mutually exclusive, either 0 or 1. But whereas coming to the quantum computing uses qubit. In short, we call it as we can also call it as in a quantum bit. So it also have two basic states, 0 and 1, and in short we call them as ket 0 and ket 1. But these states done spin up and spin down are, we can say that they move horizontally and vertically. So every state has further two states, and totally, we are going to get combinations of four different states. But again, they are not mutually exclusive, and again, they are not continuous in nature, that we can't say 0 after 1. 0 after 0 might come, 1 after 1 might come, 0 after 1 might come. So that's why they are not actually continuous in nature. And we call this as quantum entanglement. And two or more objects must be described in reference to one another when we are representing this particular quantum bits. So this particular feature makes quantum work for parallel processing, and that's where we get the more possible states by using the quantum bits, which has a limitation with the classical binary computers, the binary bits, which is just going to be limited only with the 2 bits there. Moving forward, the quantum computing power, it actually depends on the integer factorization. So it is impossible for the digital computers to factor large numbers which are the products of 2 primes for nearly equal size. Whereas quantum computer with the 2 to the power of n qubits can factor numbers with lengths of n bit binary. So this is one of the greatest advantage of using quantum computing power. And moving forward, the quantum database search. For example, to search the entire Library of Congress for one's name given an unsorted database, classical computer requires 100 years, and the quantum computer is capable of doing the same in half a second of time. So moving forward, the various practical quantum computer applications. So we say that it can be used everywhere, wherever we are in need of parallel processing, wherever we are in need of working with a huge amount of data or huge processing power, etc. So in short, to say that quantum mechanics simulations we are going to use, like physics, chemistry, material science, nanotechnology, biology, and medicine. Computers can compute millions of variables at once, and all are limited today by the low speed of quantum mechanical simulations, so that are going to get improved over the time. And the another greater application area is the cryptanalysis, so which are capable of cracking extremely complicated codes, like RSA encryption typically uses number with over 200 digits. With a classical computer, we take a lot of time to decrypt the RSA, which can be done in a very short time, and security can be enhanced. So where the quantum computers can be used for the cryptanalysis. So this is what I thought of discussing for today's session. So thank you all.